Okay, well, let's get back to it. So we'll shift gears here. We spent enough time with lenses and mirrors, so we have some other topics to kind of quickly get through here. So schematic eye. So a couple of useless facts. This is Alvar Gullstrand, the only ophthalmologist ever to win the Nobel Prize in Physiology and Medicine in 1911, and this was for his work on the dioptrics of the eye. Fun fact, he taught himself optics, and when you think about Gullstrand's contributions to ophthalmology with a very inaccurate model of the eye, and he got the Nobel Prize for that, it really should have been this guy, which is, of course, Charlie Kelman, the originator and the godfather of phacoemulsification. And whereas Gullstrand's model eye has only tortured generations of ophthalmology residents and trainees for time immemorial, Kelman actually came up with something that has saved vision and given back vision to probably millions of people with the advent of phacoemulsification. So with that as a introduction, we'll talk about the reduced schematic eye. And again, this is one of the things that you just have to kind of memorize certain numbers here. And one of the biggest numbers that we have to kind of memorize is going to be this number 17, which is the distance from the nodal point to the retina. Now, in this model of the eye, the nodal point for ray tracing is actually going to be in the eye, even though we just said earlier that the greatest refractive surface is the arterial film interface at the corneal plane over here. But nonetheless, we're going to say that the nodal point, which combines the cornea and the lens and everything like that, as if it's one thin lens, it's going to be inside the eye. So the nodal point is basically the point in the eye where all the light rays entering or leaving do not deviate. So think of it sort of like that, where the central ray will pass through. And we can see how incoming light rays, regardless of their incoming angle, will pass through the nodal point as if the cornea did not exist. So the biggest thing here, assuming you have a 22.5 millimeter axial length eye, is this magical number of 17. So you have to know this number of 17, which is the distance from the nodal point to the retina, which is defined as f prime. So you just have to know this number 17. So if we kind of take this complicated diagram and just go back and simplify this to similar triangles, we'll basically say that the nodal point is where these two triangles will connect. 17 millimeters is always going to be this fixed distance from the nodal point to the posterior focal point, which is going to be the retina. And all of these problems of schematic eye will expect you to kind of solve for one of these other three variables, because they will have given you two of these numbers, but they won't give you that number 17. So you have to know that number 17. So what you need to know out of the reduced schematic eye is this number 17. So you must know this. You can ignore many of these other things here. And you can also ignore this 5.5. Sometimes I'll ask you, how far away is something from the nodal point of the eye? Most of the times the things are going to be a few meters or a long distance away. So you can kind of ignore this 5.5 millimeters. But if they say something is actually like 6 millimeters from the eye, how far away is it from the nodal point? You may have to incorporate this 5.5 value. But for most problems, you can kind of ignore this number. Okay, so again, we're going to rebrand this as basically two similar triangles. You must memorize that 17. And when you set this up, make sure you compare similar parts of the triangle. The other thing is make sure you can keep the units consistent. I like to keep things here in millimeters for these problems, primarily because the 17 is fixed as a millimeter distance. And so then you convert everything to millimeters and then convert back if you need to, because you have to be careful. The answer choices may be in millimeters, they may be in centimeters, or they may be in meters. Okay, so let's do a sample problem here. So assume a disc diameter of 1.7 millimeters. What is the diameter of the blind spot when measured on a tangent screen 2 meters from the eye? So we know 17, that's given, that we've memorized. They've given this 1.7, so they've given us this number over here, whatever's on the retina. And then the diameter of the blind spot is what they want us to calculate, which is this value over here. And they've given us this 2 meters. So because this is so far away, we can ignore the 5.5 millimeters. That's not going to play too much of a role. But we can now set up similar triangles and solve for this over here. So we're going to give ourselves some space. Notice we've put in the 1.7 over here and the 2 meters over here. Now, it's very important that we compare similar parts of the triangle. So you can either do height over height equals base over base, but I find it's always usually easier if you do height over base of one triangle is the same as the height over the base of the other triangle. Okay, so that's going to be usually easier. So if I do height over the base, 1.7 divided by 17 is going to be the same as this height divided by this base. Note I've converted the 2 meters to 2,000 millimeters so that everything is now in millimeters. Very important that you do that because you can be sure that one of the wrong answer choices will have assumed that you just used this as a 2 and didn't change this to 2,000. Now we basically solve for x, and x is going to be 200 millimeters, or depending on whether the answer choice is given in centimeters or in meters, you can accordingly convert. You could do it with height over height equals base over base. So you could set it up as 1.7, sorry, 7. So you could do base over base or height over height. So you could do this over this equals this over this, and you'll still get the same answer, but you'll have to kind of do to get there, the math will be stickier, okay? The math is usually a bit easier if you do height over the base of one triangle is the same as the height over the base of another triangle. So just showing you method 2 works. You will kind of do some very difficult math unless you're a prodigy and can do this in your head. I can't do that in my head. Again, I'm not very smart. You may be much smarter than I am. You may be able to do this relatively easier, whereas I think it's going to be a little bit harder to do it like this. So I think it's going to be easier if you stick with method 1 over here. Let's do another example. Patient has a 3.4 millimeter diameter macular scar, blind spot measured to be 30 centimeters in diameter on a screen. How far away is the screen? Again, always draw it out. So just draw this out just to kind of give yourself 10 seconds of time to think about what are they asking you to do. So they've given us this value. We already know this never changes. And they've given us this. Now they want us to solve for this. So again, we basically can do height over the base equals the height over the base. So 3.4 divided by 17 should equal the same ratio as 30 centimeters divided by x. But note, I've converted this to millimeters so that everything is in millimeters. Okay, now we just solve for x, and x is going to be 300 divided by 0.2, and x is going to be 1,500 millimeters equals 150 centimeters equals 1.5 meters. Okay, so same concept, except instead of solving for this, they're asking us to solve for this, but it's the same thing. You're going to set up similar triangles and just kind of work your way and find what's happening. They could have also asked us a problem to solve for the size inside the eye, but they would have to give us the size outside the eye and the length outside the eye as well. Here's an example of a devious problem here, where they've given you, the units are all different, and they try to mess everything up by giving you a couple things in millimeters, a couple of things in centimeters, and you're like, wait, what exactly is happening there? So this is why I said it's very useful to convert everything into millimeters and then go from there. So this number is always going to be the same. Now they're asking us to calculate for this guy, which is the size of the blind spot inside the eye, and they've given us the blind spot size, and they've given us the the distance. So they said 0.1 meters away. So again, convert that to millimeters, 100 millimeters. Convert the 2.5 centimeters to 25 millimeters. Now we got everything in millimeters, and we can set up x over 17 equals 25 over 100. So that's going to be our ratio. We're going to solve for x. X is going to be 1 over 4. Our x over 17 equals 1 over 4. So we're going to multiply 17 times that, and we're going to get 4.25 millimeters. In other words, the size of the lesion is going to be 4.25 millimeters inside the eye over here. Okay. So that's kind of a quick run through schematic eye, and you can see that's basically similar triangles that they're asking us to solve. Okay. let's move on to what I like to call power of lenses in different media. This is also referred to as the Lensmaker equation, depending on what textbook you look at, but I find it easier to call this as power of lenses in different media. Why is that? Well, we've talked about the U plus D equals V, but the effective power of a lens also depends, we said, on the index of refraction of a given medium. So for example, if they say a 20 diopter IOL, if you written on the box, assumes that the IOL is actually bathed in aqueous. In other words, the index of refraction is 1.33. But if it is held in air, in other words, if you took a little forceps, held the IOL in the air and tried to look through it, that's not going to be a 20 diopter power. The IOL is going to have a much higher power. It's actually going to be closer to about 60 diopters in power. So the so-called Lensmaker equation may refer to multiple concepts. So in BCSC, they use it as a precursor equation to calculate the simple lens formula, which is U plus D equals V. In physics class, it's used to describe the relationship between the front and the back surface of a lens. So I'm going to use this term of what I like to call power of lenses in different media equations. So we're just going to call it the PLDME. Sorry, I don't have a clever mnemonic or type of a thing, but this is the concept that they're testing because it does have relevance, right? If you have, let's say, if you put in silicone oil into a patient's eye, how is that going to change the refraction? Because you've gone from 1.33 to, depending on the molecular weight of the silicone oil, it can be anywhere from 1.37 to 1.4, 1.5. So that's where it does have relevance for what we do. So in order to kind of talk about that, we need to figure out, well, how do we know the power, refracting power of a spherical surface? Well, this is one equation that is important to know, where that power can be basically determined by the difference in the refractive index. Okay, so the higher refractive index minus the lower refractive index, divided by the radius of the surface, which is in meters. Okay, it's just going to be in meters. So I'm going to show you this equation and show you how the math is very difficult with this particular equation. But then when you combine two of these equations, you'll actually get that the PLDME equation, or I'm going to call it the PLEDME or the PLEDME type of equation, which is going to be much more useful and much more relevant for what we're going to do and what type of things they're going to ask you on the exam. Okay, so if they ever ask you this, though, the radius of the surface, however, has to be in meters. So let's say if we wanted to figure out the refractive power in air versus underwater for the cornea. So let's say the index of refraction of the cornea is 1.37. It's not exactly accurate, but we'll just use that number. Depending on what part of the cornea you're looking at, there's different refractive indices. But we're going to say the water aqueous is 1.33, and the corneal curvature we're going to say is 0.007 meters. Now you can see, those of you who are fans of the Her Majesty's Secret Service Most Favorites spy know that that is the agent number for 007. So you can use that to remember that the corneal curvature that's used into the equation, by and large, is going to be 007 in terms of its millimeters. So if we now want to calculate the power of the cornea in water, we are now going to say the refractive power of the cornea is 1.37 minus 1.33, because basically now we're underwater, and therefore the refractive power of the cornea is only going to be about 6 diopters, which is why we see lousy underwater, because the cornea only is able to generate about 5 diopters underwater. If we do that in air, however, we can see that this is closer to about 52 diopters in air, which is why we see much better. Now you're like, wait a minute, that's the corneal power isn't, when you do keratometry measurements or get your IOL calculations for cataract surgery, you never really see a 52 diopter cornea, because you're like, wait a minute, am I dealing with a keratoconus type of a patient? Well, you can see that what those keratometers and the biometers do is they will assume the posterior corneal curvature and the power as roughly about 6 to 7 diopters, and they'll take this of the cornea there, and that's how we sort of get the average refractive power of a cornea, roughly about 44 to 45 diopters. Again, we've taken some shortcuts with the math intentionally, but just to drive home this point. But why do we go through this exercise? Is to show a couple of things, because this is almost close to 0. right? This is 007, this is close to 0. So the power of refractive surface really depends on the index of refraction. That's why we said the power of the lenses based on the media, the lens can have extremely different different powers. So because R is usually small, we can ignore it for most of these, and we can combine with two of these equations in order to form the Plead-Me equation, and this leads us to this Plead-Me equation. So basically, we've combined two of these equations together. We've gotten rid of R because R is basically 0, and we're saying that if we take the power, if we know the power of the lens in one medium, we can figure out the power of the lens in a different medium. So this is really what we've done. We've set up a ratio to compare the refractive power of the lens based on the index of refraction and gotten rid of the radius of curvature. Now, when setting up this type of equation, be careful that you match up the power of a given medium in the same row as that particular index of refraction. And again, if the math gets too tricky or difficult, we've probably set up the equation wrong. Okay, let's do an example of one of these types of problems. PMMA IOL, N of 1.49, has a power of 24 diopters when measured underwater. What is the power of this lens in air? Well, this is a great example of a type of problem that can show up on the test. And this is where we can use the Plead-Me to figure that out. So we set up the Plead-Me as this. So they want us to figure out the power of this lens in air. They've given us the power in the fluid. We know the index of refraction of the IOL. We know air, that's 1.0. And we know that underwater, which is 1.33. So you have to memorize a 1.33 as well. So really what we're going to do is they want us to solve for this. They've given us all of these other values. So we're primarily just going to do 49. This is going to be 49. This is going to be roughly 16. That's going to be roughly about 3. So 24 times 3, that's going to be about 72. So basically, this lens, which has 24 diopters underwater, is going to have about 72 diopters of power in air. So that's what I said earlier on. If you take a 20 diopter lens and take a forceps and hold it up to your eye and try to look through it, that's going to be about 60 diopters of power. So similarly, of a 24 diopter lens, that's going to be about 72 diopters of power in air. Okay, so you can see how we are using the difference in the index of refraction to figure out how much power does this lens now have when we change the media from where, change the media between the two surfaces, or between the two substances there. Okay, let's use another example here. Prescription swimming glasses made from plastic, -2 diopters in air. What is the power of the goggles in water? So again, we set up the same Plead-Me. So air over air or fluid equals the N of glasses, which is 1.44. They've given us that. We know the power in air, so the index of refraction of air. We know that of water, 1.33. So again, we set it up the same exact way, okay? So except this time we're solving for this over here. So when we solve for this, this is going to be approximately 4.4. So we're going to do 0.44 divided by 0.11. So we're going to get 4 over here. So -2 divided by P equals 4. Hold on 1 second, guys. And this is actually my fellow. Give me 1 second. Just texting me something regarding a patient. Okay, I'll call him back during the break. It's not important. Okay, so when we now want to figure out the power of the goggles in water, we know that this is 4, and this is -2 divided by x is going to equal 4. So the power is going to be -0.5 diopters in water. Okay, now bonus points. What was the flawed premise of this question? Well, because in other words, does this say that if we get these fancy pants, -2 diopter prescription swimming goggles made from plastic, we put them on, now we go swimming, that these goggles are only going to be -0.5 diopters in water? Well, no, because what we're assuming is that we have a good suction cup. We've got air between the glasses and our eye. And so those will actually function as -2 diopters in water as well too. But if water got into the goggle, that's why I said the power of the goggles in water, if water got into the goggles between the face and the goggles, then the power of the goggles is going to dramatically change, and those goggles are only going to be about -0.5 diopter in water. Okay. This is kind of another type of a question that you can get similar based off of this concept here. And again, does actually have some clinical relevance. So let's look at this. So we have an IOL constructed of a novel material, 1.69. So this must be something quite experimental because, as I said, the highest index of refraction that we have of a acrylic lens of 1.55. So we have a 1.69, this novel material. And if we're given an 18 diopter IOL of this material, and you put it in the capsular bag, but it's bathed in aqueous, but later this IOL falls into the vitreous cavity that is filled with silicone oil, what will the effective power of the IOL be? Well, now we do the power of the IOL in aqueous, in other words, when it is in the capsular bag, divided by the power of it when it's now in the quote unquote vitreous, but keeping in mind that the vitreous is now actually silicone oil. Now we can actually figure out, they're asking us to solve for this based on these different values. They've given us the N of the IOL, which is 1.69. We know that the aqueous is 1.33, and the N of the vitreous, which is going to be 1.37, that is this index of refraction. So now what we do is we're going to accordingly solve for the missing value. Okay, so we're going to have 18 divided by P of vitreous equals 1.69 minus 1.33 divided by 1.69 minus 1.37. Okay, because in other words, the silicone oil is actually this new vitreous over here. And when we solve for that, we're going to get roughly 9/8 on this side and 18 over here. So when we try to now divide 18 divided by 9 divided by 8, this is going to be 16 diopters. So basically this lens is now going to have about only 16 diopters of power if it falls into the, or just kind of, if, well, not even if it falls into the vitreous, even let's just say the silicone oil were now to come over it, for example, we have now had a 2 diopter hyperopic shift, though we should probably get this lens out rather than worry about the optics, because at this point, you know, this may cause a retinal tear, or detachment, or UGG or something like that. But that would be how we would solve that for the purposes of optics. This one is one of those where, again, you can solve this on your own. I don't think this would come up on the exam. This is where you have to try to figure out the index of refraction, and you can see the math for this will be very difficult. If you do it right, that this index of refraction will be about 1.44, so maybe this IOL is made of silicone. I won't worry too much about this because if you're trying to do the math, you may feel like this guy and just want to chuck your laptop outside the window, so please don't do that. Lens maker's formula, again, is going to be sort of on your own. This would be used to construct a lens with a specified focal length, and that's where you have to kind of keep in mind the refractive index, the radius of curvature of each surface, and then you can calculate the focal length of that particular lens. So again, you can sort of read this on your own and see how you would solve that. Again, I won't waste too much time because, again, you can see how difficult and complex this math can be. It's as disgusting to try to even solve by hand. And this was the best, easiest example that I could even come up with when trying to solve this. So again, you can kind of do this on your own, but let's move on to something which is a bit more relevant. And this is extremely relevant, which is lens effectivity, which is, we've said now previously, the power of the lens depends on things like the radius of curvature, the lens thickness, and the index of refraction. That's the thick lens stuff that we talked about. However, one assumption we have made is that the given lens is held at a certain distance from the eye in order to maintain this dioptric power. So in other words, if we have a +5 diopter lens, if we hold the lens super far away from the eye versus super close to the eye, that 5 diopter lens will effectively have different power based on where it is held from the eye. So if we move it further away or closer to the eye, it's not going to function as a 5 diopter lens. That assumption of a 5 diopter lens assumes that you hold it at a certain distance. And that's why for example, when we do eyeglasses, that vertex distance is so important, because if you have a patient now, if you have a low prescription, the vertex distance probably makes no much difference. So if you're just prescribing like a -1 pair of glasses, you get away with the 12.5 vertex distance, and it makes really not much difference. But let's say you've got a patient with unique anatomy or extremely high prescriptions, the vertex distance can make a big difference. And that's one of the reasons they like asking about this concept of lens effectivity. So I like to think of now the analogy of Pinocchio, where you've got a long nose, right? And you can kind of move the lens either forward or backward along the nose. So if we move a lens forward, think about it, just means to move it sort of down along the nose away from the eye. So moving a lens forward means moving it away from the eye, whereas moving a lens backward means moving it closer to the eye. So just think of this diagram whenever we use this terminology of moving a lens forward, because I've had students come and ask me like, wait a minute, when we move a lens forward, doesn't that mean we're pushing it up closer to the eye? But by convention, this is what that terminology means, is moving a lens forward. It's just think Pinocchio, moving the lens away from the eye. Moving a lens backwards means moving it closer to the nose. So when we move a plus lens forward, in other words, down along the nose, that plus lens is going to gain more plus power. So a +2 diopter lens will gain additional plus power if pushed down along the nose. So to maintain proper distance correction, a plus lens may have to be decreased in power if it is moved forward. But a plus lens, if we move it towards the eye, decreases its effective plus power. So a 3 diopter lens, if you shift it closer to the eye, it's going to function like a +2 diopter lens if pushed up on the nose. Therefore, the lens must be increased in power in order to maintain the same correction for distance. So again, this explains why a hyperope has to wear higher powered, in other words, higher number contact lenses as compared to their glasses. So if you have a +5 hyperope, they're going to probably wear like +6 diopter contact lenses as compared to like those of you who are myopic. So I'm a -6. This is much easier for me to understand. So I'm wearing a -6 in my glasses, but when I wear my contact lenses, it's going to be about a -550. So I need less power as a myope on my eye, because effectively when I wear a contact lens, I need less minus power, but in my glasses, I need more minus power. So that segues into moving minus lenses forward will decrease the effective minus power. In other words, it adds effective plus power. So you see in both of these, where if we move the glasses down along the nose, we've increased the effective plus power, whether it's a minus lens or whether it's a plus lens. So this is why presbyopic myopes may do this to kind of give themselves reading glasses where you're kind of decreasing some of the minus power and giving yourself a little bit of plus power. Now, moving minus lenses towards the eye increases the effective minus power. So again, a -3 diopter lens will behave like a -4 diopter lens if pushed up along the nose. So this is why you'll see young kids or teenagers, if they're uncorrected or undercorrected, they'll constantly be pushing their glasses closer to their face in order to give themselves more myopic correction. So again, those of you who grew up wearing glasses from a very young age, I recall, I think there was like this a good 3 to 4 months of time when I was in 4th grade. I definitely think I was undercorrected because I constantly was like doing this, pushing my glasses closer to my nose, closer to my eye, not realizing what I was doing. But you can see that's a subconscious thing that you're doing to try to bring it closer to the eye. In fact, I would sometimes do this in 4th grade, where I would take my glasses and bring them even closer. So I definitely think I was under minus, or maybe I was just accommodating too much and I just liked to accommodate. But in any case, that that behavior is a compensatory mechanism because of lens effectivity that you'll see in patients. So where will they test you on this in terms of the exam? Well, a lot of times they like testing when you're going from glasses to contact lenses or contact lenses to glasses. Really, we're changing the focal length of the lens by taking into account for the vertex distance. Well, we already know what the formula for focal length is going to be, 1 over the power of the lens. So let's say if we have a 5 diopter lens, we're going to do 1 divided by 5 is going to give us 0.2 meters as the focal length. Again, I've told you about using 100. But when we go from glasses to contact lenses, we need to subtract the vertex distance. Remember, when you're using glasses, you have a vertex distance built into the glasses. But when we're going to contact lenses, we're going to subtract the vertex distance. Similarly, when going from contact lenses to glasses, we are going to add the vertex distance. So we're going to have to take that into consideration as well. So let's do a problem. Patient wears +10 diopter glasses at a vertex distance of 10 millimeters. What power contact lenses should be ordered? Well, what can we say about the answer choices even before we do any math? Well, this is a hyperope. We just said that the hyperope is going to need more power in the contact lenses as compared to when they're wearing their glasses. So we know right off the bat, answer choice A is going to be incorrect. That person's not going to need less power in their contact lenses. They're actually going to need they're going to need more plus power. So we can safely eliminate A as one of the answer choices, probably even eliminate B because it's like a +10. So now we've given ourselves from a 20% chance of guessing correctly to a 33% chance by getting rid of A and B. But we don't want to go through life through percentages, so we should actually do the problem here. So same problem there. How are we going to set it up? Well, we need to basically figure out what is the focal length of the glasses, and keeping in mind that the vertex distance, the lens effectivity, is playing a role. So the focal length of the glasses is going to be 100 divided by 10, that's 10 centimeters. But now we're going from glasses to contact lenses, so we need to subtract the vertex distance. In other words, the focal length of the contact lenses should be the focal length of the glasses minus the vertex distance. So now we know that the focal length of the contact lenses is now going to be the focal length of the glasses, which is 10, minus 1 centimeter is going to, because that's the vertex distance. 10 millimeters is the same as 1 centimeter. So the focal length of the contact lenses is actually going to be 9 centimeters. So now in order to figure out the power of the contact lens, we're going to do 100 divided by 9, and that's going to give us approximately 11 diopters for the contact lenses, which was, I think, answer choice D. There you go, answer choice D. So that's going to be the correct answer. Okay, so that's a simple problem that shows how we have to now subtract the vertex distance because we are going from glasses to contact lenses. Similarly, if we now go from contacts to glasses, we now have to add a vertex distance. And it looks like this patient has a little bit larger vertex distance of 14 millimeters. So now what can we say about the answer choices even before doing the math? Well, we know that this patient is at -8 in their contact lenses. They're not going to need that much power. I'm sorry, excuse me. They're going to need more minus power in their glasses as compared to the contact lenses. Again, you get rid of choice A and choice B and realize that we're dealing with one of these other choices here, either C, D, or E. So let's solve for this. We have -8 diopter contact lenses. So what is the focal length of the contact lens? So 100 divided by -8 is going to be -12.5 centimeters. But because we are going from glasses to contact lenses, we're going from, what are we doing? We're going from contact lenses to glasses. So the focal length of the glasses are going to be the focal length of the contact lenses plus the vertex distance, okay? Plus the vertex distance. So we have -12.5 centimeters as the focal length of the contact lenses. Now we need to add the vertex distance, which is 14 millimeters. So -12.5 plus 1.4, that's going to give us a focal length of -11 centimeters. Now we can easily calculate the power of the glasses. 100 divided by -11 is going to give us roughly -9, and therefore the answer choice E is going to be the correct answer. Okay. Something a little trickier. A +5 diopter hyperope is given a +4 lens. How far in front of the cornea must he hold it in order to see clearly at distance? So again, don't panic. All we really have to do is figure out the focal length of the eye and the focal length of the lens. so that this +4 diopter lens can sort of act like a +5 diopter lens. So let's calculate the focal length first of this lens. So the focal length of the lens is going to be 100 divided by 4, which is going to be 25 centimeters. So that's the focal length of the lens. Well, for the eye, this is a 5 diopter hyperope. We know that this is going to be a 20 centimeter focal length. So now we basically have to match up the focal distances. So the vertex distance is going to be 25 minus 20 equals 5 centimeters in front of the eye. So in other words, this patient can get this, even though he or she is a 5 diopter hyperope, and we've given them a 4 diopter lens, if that person holds it 5 centimeters in front of the eye, this 4 diopter lens can kind of act like a 5 diopter lens. And that makes sense. We said when you move the lens away from the eye, it's going to gain plus power. Okay, it's going to gain additional plus power. Here's another way of looking at that same problem. We can also look at it like this, because some people have said, well, I kind of don't understand this thing. I kind of understand the concept of the far point. Well, we know that the far point of this eye, because it's a hyperope, is going to be behind the eye, right? So a hyperope is a +5. The far point is going to be 20 centimeters behind the eye. Now we're going to say, well, how can we get this lens so that the secondary focal point of this lens matches up with the far point of the eye? So we know that if the lens is 4, well, its secondary focal point is 25 centimeters to the right of the lens. So we want this 25 centimeters to match up with this 20 centimeters of the eye. So therefore, the distance between these two have to be 5 centimeters. Okay. So again, you can see how it's the same way, it's the same problem, but there's 2 different methods of solving that. And again, I don't care how you, which one you prefer, I just want you to get it correct. All right, one more problem here. So what power contact lens, this is the type of a problem you're probably more likely to see on the exam. What power contact lens would you need for a patient who wears +12.5 diopter glasses? Vertex distance of 13 millimeters. This is now going to involve a little bit of thinking, a little bit of math. So we know that this is a patient who wears +12.5 diopter glasses with a vertex distance of 13. So let's find the far point. This is a hyperope. So 100 divided by 12 is going to be 8 centimeters or 80 millimeters behind the eye. But it's going to be, this should actually be 80 millimeters behind this lens. I apologize. That should be behind the lens. I keep forgetting to, what slide is slide 172? 172 should be behind the lens. So we have now the secondary focal point of this lens, which is 80 millimeters over here. Now we basically want to figure out, well, what is this patient's exact far point if we were to put a lens on the eye such that the secondary focal point of that lens matches up with this far point? Well, we got to get rid of this 13 millimeter vertex distance. So we get rid of the 13 millimeter vertex distance. And now we realize the distance from the patient's cornea to the far point is going to be 67 millimeters, AKA 6.7 centimeters. And now we can basically divide 100 divided by 6.7 in order to get the focal point of the eye. And that's going to be 15 diopters. It's going to be about 14.92 diopters. We're going to round up and say that this patient is going to need a 15 diopter contact lens. And again, that makes sense because if they're wearing 12 in their glasses, well, they're going to need more power in the contact lens, and that's where we're going to get the 15. Okay. Okay. Any questions here? There have not been any questions so far, so I hopefully people are still awake, or everybody is understanding everything perfectly. So I will assume it's somewhere in the middle of those two things. All right, let's talk a little bit about magnification and telescopes in the time that we have here left before lunch. So magnification. Well, we previously talked about linear magnification, aka transverse magnification, which is during the U plus D equals V problems. Now there's also axial magnification, angular magnification, and magnification from a simple magnifier. So three other types of magnification that we have to talk about. So axial magnification is also known as longitudinal magnification. And what it means is that there's magnification along an axis between two conjugate points. So we just really represented this as a two-dimensional thing, but there's also a three-dimensional component to it. So you can read a longer definition of it, but if you want a short definition of it and a short practical example, the square of the transverse magnification is going to be basically your axial magnification. So in other words, if we solve a U plus D equals V problem, and they tell us that the linear magnification is, let's say, 6, the transverse magnification is going to be double that, excuse me, not the double that, it's going to be the square of that, which is going to be 36. We're like, why do we care about axial magnification? Well, axial magnification causes distortion of 3D images. So for example, if we were to look at the height of a retinal detachment, axial magnification will help to offset some of the loss of the stereo acuity that's caused by an indirect ophthalmoscope. So for example, let's say we have a PD of 60 millimeters. When we look through the ophthalmoscope, the indirect, the PD is effectively reduced down to 15 millimeters. So right off the bat, we've lost 4-fold of the stereopsis when using the indirect. But the axial magnification will compensate. Let's say we're using a 20 diopter lens, and we're going to use Goldstrand's eye of 60 diopter power. Again, these are all gross simplifications. So 60 divided by 20 is going to give us a 3x magnification if we do big movie. But axial magnification tells us we actually are going to get 9x magnification. And so the 9x magnification divided by the 4-fold reduction tells us that we are going to get about a 2.25x magnification when we are looking at this patient's retinal detachment. So basically, when we look at the retina with the 20 diopter lens, with these numbers that we've given here, we're going to get about a 2 to 2.5x magnification when using the 20 diopter lens. Okay, so you can see again, this is why there is some relevance to what we do. But let's talk about how it's going to show up on the exam. Object is located at an unknown distance from an unknown lens, and it forms an image to the right of the lens at a distance that is 5 times the distance of the object from the lens. My goodness, that is a lot of words. So this is why let's just draw it out. So basically, we are saying we have a U and we have a V, so little u and little v. And we know that the image distance from the lens is 5 times the object distance from the lens, which is u. So in other words, v equals 5u, right? So whether it's 1 centimeter, 2 centimeters, whatever it is in this case, the little v is 5 times the value of little u. So we can use our little v equation. So it's really a 5x magnification transversely. But if we do axial magnification, it's actually going to be 25x when we take into component the axial component of sort of the height of it as well. So it's sort of 3-dimensional type of magnification. Okay, that's going to be the more important one to kind of keep in mind here. Angular magnification, I want you to read on your own because it has to do with angles rather than distances, but why bother with it? So for example, if you look at the moon, which is about 0.5 degrees to the unaided eye, but then because you look at it with the telescope, it's going to increase. You're going to have a 10x magnification of the moon because of angular magnification. So angular magnification is primarily going to deal with telescopes. We're going to spend a little bit of time talking about telescopes in the next couple of slides here, but that's what angular magnification does. Again, magnification from a simple magnifier, a very busy slide, you can read that, but basically angular magnification by convention says if you were to use a lens and hold it 25 centimeters away from an object, how much magnification can we get? So it's essentially we're going to divide that by 4. So we're going to get, whatever the power of that lens, we're going to divide it by 4. So for example, you have a 20 diopter lens and you hold it 25 centimeters from the patient's eye, how much magnification can you get? So you're going to get 20 divided by 4, and that'll give you about a 5x magnification, of the patient's eye. So this was what we call the inpatient consult resident slit lamp. You can use the 20 diopter lens to examine a patient's eye if you don't have access to a handheld slit lamp. Okay. Let's shift gears here to talk about telescopes in the 20 minutes or so we have before lunch. So we've got two main types of telescopes, an astronomical telescope and a Galilean telescope. This kind of is taken from Pirates of Caribbean, of course. And you can see that the telescope that Johnny Depp is holding is, the focal lengths of this could have been, the lenses could have been chosen better. And that way you wouldn't have had such a long, obnoxious telescope that's so long. The telescope that the guy on his left, I forgot that character's name, is holding is a much more normal distance length telescope because it's probably using lenses that are more appropriately powered. Those of you who think, oh, it's too difficult for me to figure out how to use telescopes and stuff, this is actually from the children's section of the Field Museum in Chicago. So you can see that they're teaching kids how to use telescopes about, Galilean versus astronomical telescopes. So if your child can learn it, you can learn it too. All right, let's talk a little bit about some terminology here. So the objective lens is the lens that is closer to the object of interest. In other words, further away from you. The eyepiece lens is the lens that you, as the observer, look through. So if we have an astronomical telescope, which is also known as a Keplerian telescope, it's going to form an inverted image always. It's going to be the combination of two plus lenses that are put together. And these lenses are going to be lined up in such a way that the secondary focal point of the eyepiece is going to match up with the primary focal point of the objective, so that there's going to be an intermediate image plane. Okay, so here's our eye, we're looking. And the reason you can remember with an astronomical telescope, if you look at the planet Mars, do you really care whether it's upside down or right side up? If you can see it, you can see it. That's great. So if you were to use an astronomical telescope, the Martian on Mars would actually be inverted. Okay. Fun fact: the slit lamp is basically an astronomical telescope, but it actually has a re-inverting prism, which is known as a Porro-Abbe prism, which then re-inverts the image in order to get an upright image. So those of you who are like, I don't want to know about telescopes, well, every time you use a slit lamp, we are using an astronomical telescope. A Galilean telescope is going to give us an upright image. It is more frequently used in ophthalmic optics, such as in loupes. And it's preferred for visual aids because they are shorter and lighter than Keplerian. It is going to be a combination of a plus lens and a minus lens. So here we have the patient or the observer. So we're going to have the secondary focal point of the minus lens, which is in front of the eye, to line up with the primary focal point of the plus lens over here, and the intermediate image plane is going to form over here. Okay, so the focal point is going to coincide in the intermediate image plane. With a Galilean telescope, the eyepiece is always going to be minus. Okay, and you obviously want to have a higher power for the minus lens than the plus lens. Same thing with a Keplerian telescope or an astronomical telescope. The numerical value of the eyepiece should be higher than the numerical value of the objective. Otherwise, you'll get a non-magnified image. And that's what this equation down here is telling us, because magnification of a telescope is the power of the eyepiece over the power of the objective. So you want to have a stronger numerical value, whether it is an astronomical or a Galilean versus the objective, so that you'll get more magnification. And so the higher the difference between these two numbers, the greater amount of magnification you'll get. Now, if you end up using the lower powered lens as the eyepiece and the higher power lens as the objective, again, whether it's Galilean or astronomical, you won't get magnification, you'll actually get minification. And that's going to be an important thing to think about when we talk about why is it that myopes who are over minus will complain that things look too small, as compared to hyperopes who will notice that things are much bigger. So to summarize about telescopes here before we do some problems, astronomical telescopes, aka Keplerian telescopes, are going to have a positive eyepiece and a positive objective. The images are going to be inverted. So if you think of the mnemonic here for astronomical and think that the plus sign is instead of the T, that's going to remind you that it's going to be two plus lenses that are put together. The A reminds you that it's going to be an ass backwards, aka an inverted image. Galilean telescopes are going to have a minus eyepiece and a positive objective. The images are going to be upright. You can think mnemonic. Galileo was a good guy, right? He was an upright guy. Think of the G, therefore, as an I, and you can also think of this horizontal mark in the G as a minus sign, which is going to be the eyepiece power. Again, those are silly mnemonics. If you can just think about what you're trying to do about the image planes and the primary focal point, secondary focal point, et cetera, that's probably the more scientific and correct way to do it. But if you have just want to understand it, just think of these mnemonics about the ass backwards and Galileo being a good guy, and hopefully you'll remember which one is going to be which in terms of the power of the lenses to be used. All right, some other rules about telescopes. The magnification is going to be minus the eyepiece over the objective. Okay, so now this just reminds us that for Galilean telescopes, we're going to have a minus eyepiece power. So if you put a minus along with a minus, you're going to get a positive value to remind you that the image is going to be upright. Whereas with a Keplerian telescope, remember, we're always going to get an inverted image. So we're going to get a positive number and a positive number here, but because you got a minus here, we're going to get a minus value to remind us that it's inverted. Okay. The distance between the two lenses must be the sums of their focal points. So the focal point of lens 1 plus the focal point of lens 2 is going to be the distance between the two lenses for construction of the telescope. And we just said this here about the secondary focal point of the first lens must coincide with the primary focal point of the second lens. Okay, let's do an actual problem. So telescope is constructed with a plus 20 diopter lens and a plus 5 diopter lens. So right off the bat, we know that this has to be an astronomical telescope because we only have 2 plus lenses. And if we want this to be a useful astronomical telescope, the higher power lens has to be the eyepiece. In other words, the 20 diopter lens has to be our eyepiece. The 5 has to be the objective. If we construct this telescope correctly, the magnification is going to be the power of the eyepiece over the power of the objective. We can stick a minus sign there. So we can do minus 20 divided by 5 is going to give us minus 4x mag. That tells us that we're inverted, not that we are minified. Okay, so inverted, not that we are minified. But now we want to figure out the distance between these two lenses. So what we want to do is we're going to figure out the focal length of the first lens, the focal length of the second lens, and make sure that they are kept apart so that if we are looking, so here's our eye, here's our eyeball right over here to the left of this lens. We want the secondary focal point of the eyepiece to match up with the primary focal point of the objective. Okay, so we're going to do 100 divided by 5, 100 divided by 20, 100 divided by 5, that's going to give us 5 and 20 respectively, ironically enough. 5 plus 25 now is going to tell us that we are going to give 5 plus 20 to give us 25 is going to tell us that 25 centimeters is how far apart these lenses should be in order to yield a useful image. Okay, so you get 4x magnification, 25 centimeters apart as the focal length, and this will give us a useful telescope. Here's another question about an astronomical telescope, except they've given us the power of the eyepiece, and they're asking us to calculate the power of the objective. So again, it's the same concept, except they're asking us this now from sort of the reverse angle. So what is the power of the objective lens that they want to know? So, well, we know the lenses are 43 centimeters apart. So let's first calculate the focal length of the eyepiece. Well, they told us the eyepiece is going to be 10. So 100 divided by 10 tells us that this also has to be 10 centimeters. Therefore, this length has to be 33 centimeters, because if this whole thing is 43, this is 10 over here, well, this has to be 33 over here. So 43 minus 10 is going to give us 33 centimeters. So now we know the focal length. And how can we determine the power of this particular lens? Well, we do 100 divided by 33 in order to determine the power of this lens. And lo and behold, if this unknown lens has a focal length of 33 centimeters, well, the power of this lens should be now 3 diopters. Okay, 3 diopters of this objective. They didn't ask us this, but if you wanted to figure out what is the magnification of this lens, well, 10 divided by 3 is going to be about 3.33x magnification. Here's a problem now using a Galilean telescope. Telescope was constructed +5 and a -10. What is the magnification? How far apart are the lenses? So again, for the we know that because we're given a minus lens, this has to be a Galilean telescope, and you'll want to use the minus lens as the eyepiece, obviously, and this is going to be our objective. So magnification equals the power, the minus the power of the eyepiece over the objective. So like a minus 10 divided by 5. Again, you can just get rid of the minus if that makes it easier. So 10 divided by 5. This gives us a 2x magnification. Now, we have a plus sign because we have an upright image. Remember, this is a Galilean telescope, and Galileo was a good guy. He was upright. So we're going to get an upright image in addition to the magnification of a 2x magnification. Now, the secondary focal point of this first lens, which is over here, must coincide with the primary focal point of the second lens, which is over here. So they want us to know how far apart are these two particular lenses. So we know that the focal point of the first lens and the focal point of the second lens, so 100 divided by 5, 100 divided by -10. So here is the focal length of the first lens, which is 100 divided by 10 is going to be 10 over here. And 100 divided by 5 is 20 over here. So we want these to kind of line up. So in order for them to line up over here, the distance between these two lenses has to also now be 10 centimeters apart. Another problem, if you're given 25 diopter lens and an unknown power lens to create a functional telescope such that the lenses are 6 centimeters apart, what is the power of the unknown lens? What is the magnification of this telescope? So again, we know this must likely be a Galilean telescope, given that one of the lenses is minus. First, start off by calculating the focal length of the eyepiece. So 100 divided by -25 is going to give us, quote unquote, a -4 centimeters. So the distance between the two lenses must be the focal length of the first lens plus the focal length of the second lens. So they want us to calculate the, and we know, they know that the create a functional telescope. So the lenses are 6 centimeters apart. So we know that 6 centimeters apart, 6 equals -4 plus the focal length of the second lens. So we bring the 4 over here. Focal length of the second lens must be 10. So therefore, this must be the power of the objective lens as 10. Magnification is going to be minus the eyepiece over the objective, and it's going to give us a 2.5x magnification. Okay, so that's telescopes. Let's talk a few clinical examples here. The over minus myope. Why is it that we say that, myopes eat minus? Well, because they're able to accommodate, they may favor more and more minus power outside the eye. And so if you have more and more power outside the eye, when you accommodate, the patient generates more power inside the eye. So they have more plus power inside the eye. So basically now they're looking at the world through a reverse Galilean telescope. So they may say the image is sharp, but it will be minified. So that's an example of clinical relevance of this concept. Aphakic or a high hyperope magnification. When the lens is removed and not replaced with an IOL, basically patient has extra minus power inside the eye. And then when he or she wears glasses outside the eye, it's going to require a plus lens. So they have a minus lens inside the eye, plus lens outside the eye. They've now basically gotten a Galilean telescope. For example, if you have a somebody who's a plus 10 aphakic lens outside the eye, minus 12 extra power inside the eye, they're going to look at the world with a 1.25x magnification, primarily because they have a Galilean telescope. Again, you're like, why do I care about this? Well, sometimes if you have a long-standing hyperope, you have to caution them that if you make them plano after cataract surgery for a couple of months, they may feel what's described as a Lilliputian effect. Where if you think back to Gulliver's Travels and when he goes to the land of Lilliput, where everything looks smaller. So even though they're seeing the world now normal size to you and me, for them, the world has become smaller. So it's really important to have this discussion beforehand I did somebody the other day who was like a 19 axial length. They were like a +8 or a +9 or something like that. We had this conversation, but when I did her first eye versus the second eye, the in between, and we thankfully we spaced them just 1 week apart. She was really miserable. Like post-op day one, she was seeing fine, but she was like, "Oh my gosh, like I'm glad you told me because everything looks so much smaller." So it's really important to have this discussion with patients before cataract surgery, so that even though you've made them plano, again, nothing to be said about the challenges of doing cataract surgery in a short axial length eye with risks of choroidals and small anterior chamber and all of that type of stuff. But you may now have this unhappy patient afterwards if you don't have this conversation sort of before it. This just shows what this previous slide said. So if you have an aphakic, let's say that he or she is wearing a 10 diopter lens outside the eye in their glasses, they've got an extra -12.5 inside the eye. If we now do the magnification, this is now their eyepiece that's inside the eye. The objective is basically outside the eye, so 12.5 divided by 10, they're going to see the world 25% enlarged. But let's say we fit the same patient, just to make the math easier. Let's say we fit them with a 11.75 diopter contact lens. Now, when we look at the magnification, things are only going to be 6% enlarged. So this is one of the reasons why if you have somebody who's an aphakic a patient, like a child, a contact lens may be much more tolerable than wearing the high hyperopic glasses because of you've decreased the magnification. This now leads us to talk about the anisometropia and anisoconia. So remember, as long as the quantitative value of the refractive error is about between 3 diopters between each eye, the patient will not experience any subjective image size distortion. Anisometropia happens primarily more than 3 diopters, and anisometropia is a problem on paper. And simply anisometropia means that there's a refractive error between each eye greater than 3 diopters. Anisoconia is when the patient is unhappy, because what happens is, remember, every 1 diopter of hyperopia gives you about a 2 to 3% magnification relative to the other eye. So patients can tolerate about a 6 to 7% size difference, but when things are more than that, then they're not going to be able to tolerate about a 10% difference between the 2 eyes. They're going to be unhappy. Again, not a problem for kids. Always give the full refractive error because, first of all, kids can be more adjusting than adults, but we don't want to, in order to kind of combat anisometropia and anisoconia, not give them the full cycloplegic refractive error, because amblyopia is the bigger enemy than anisometropia and anisoconia. So remember, we don't want to cause amblyopia. We will live with anisometropia and anisoconia. We don't want to have to deal with amblyopia. This is just a spectacle example here. So if you have a patient wearing a -3 lens in the right eye, +1 in the left eye, things are going to be about 6% smaller in the right eye, about 2% larger in the right eye. This patient is going to feel things are about 8% larger in the left eye, and they're going to have about 8% of anisoconia and going to be unhappy. An adult patient can tolerate this. Unlikely that an adult patient will tolerate this. A child usually is able to tolerate this, as I mentioned here. A couple of miscellaneous magnification notes. So we talked about using something as a simple magnifier. So they were giving you an example. How much magnification will a 24 diopter lens give if used as a simple magnifier? So again, we said we have to hold this at 25 centimeters. Again, who cares about the math as to why they decided 25 centimeters was the thing? Again, you can look at optics textbooks that talk about why they've come up with that as a standard closed distance. But if you use this 24 diopter lens, hold it about 25 centimeters away from the object of interest. So all you have to do is divide 24 divided by 4, and you're going to get a 6x magnification for this patient. Okay. All right. Presbyopia and accommodation, that's going to take us a while to kind of get through. So what we'll do here is we'll go ahead and pause for lunch here.